we're going to evaluate the transient analysis for an RL circuit, or RL in series at this stage. Let's go ahead and fire up LT-Spice. We will start a new blank schematic. Let me make this a little big so we can actually see what we're doing here. I think this is plenty of screen space. I like to start by drawing my wires, okay? Knowing this is going to be a rectangular shaped circuit. So I'm going to click here, click here, click here, and then finally click here and hit the escape key. Good. Now we're going to put our components. I'm going to put a resistor here, an inductor here, and the AC generator over here. Right mouse click, go to component, draft component. I'm going to start with a resistor. Okay, as you can see, I didn't even complete the word and the resistor appears. So I'm going to say, okay, I can put it anywhere, but right now it's in the wrong direction. Hold the command key and R at the same time, and it will flip it for it. So I'm just going to put it right here. Move my mouse, don't click on anything. Now, if you do, you're going to have to delete that second resistor. Okay. Now, let's say I made a mistake and I clicked here, and I got a bunch of resistors. Okay. No need to panic. Hit escape. Go back. And what you're going to do is you're going to be going to edit, and you go to delete. You see F5 here. There's a scissor. Take it out. Take it out. Okay. Good. Now we're going to introduce an inductor over here. So I'm going to go to draft component. Okay. And I'm going to type inductor. And as you can see, it figured what I was trying to do. I'm going to say okay. And I'm going to insert it right here. Again, I didn't click the mouse, so I don't need an extra inductor. Hit the escape key. I need a voltage source here, right? So a power supply. So I'm going to right mouse click again, draft, component, just type voltage. And notice I didn't even finish. It's going to ask me, do you want a voltage source that is either DC, AC? I'm just going to say okay, and I'll set it myself to what I want. So put it in here, right here, then hit escape, and I'm not drawing any other one. One more thing you might want to do in your circuit, you should, is put a ground if you're going to run an analysis, right? So if you're going to do a transient analysis or an AC analysis, you will always need a ground or a point of reference in LT-Spice. So I'm going to right mouse click again, draft, go to net name, and then pick a ground right here and put it right here. Okay. And just draw a line now, which is basically a wire from the circuit to the ground. Then hit escape. Okay. Now we've finished drafting our circuit. So now let's put some values. Let's start with the easiest one, the resistor. And in here, I am going to put a 10 ohm, okay, for this example. For your inductor, the only value you can enter right now, and I'm not going to do a real inductor, I'm going to do what we call an ideal conductor. So you only need the Henry value for this inductor. I don't need an internal resistance for it or an internal capacitance, because all these components actually do exist. Or are real within an inductor. So it is a model, in other words. But we're simplifying this model where it's a pure inductor. So I'm going to right mouse click here and type 2 millihenries. Okay. All right. So now, how about our power supply? If you click, right mouse click here, you notice it tends to want you to enter a DC value for this. I'm going to hit advanced since I want a sine wave, and I will pick a sine wave. So right here now, you will pick a sine wave. And if you do pick a sine wave, you need an amplitude. I need 10 volt peak. I want an offset 0, so I don't have a DC component to this, right? So I'm not shifting it up or down. And I want, at this stage, 60 hertz to get started. Okay? We'll leave these attributes here alone. Go straight down here, again, 10 volts. And put a phase shift of 0 degrees. Right? So we don't want to shift by a certain angle. So that means your power supply really starts at 0.00. Okay? And I'm going to hit OK. There you have it. Now we're ready to set up the properties for the actual simulation. Because if I click on simulation right now, I'll get no analysis command found. So you need to create a command. To do this, right mouse click anywhere and go to draft again. And then you're going to go to what we call Spice Directive. Okay? So in the Spice Directive, this is where you write your directive, right? So let's say you don't know how to write a transient directive. Well, you can get help. So you can right mouse click here, help me edit. And then you're going to go to analysis command. And notice by default is that transient. Okay, so what do we want? In the transient, I'm going to simulate as if I'm using an oscilloscope to look at the circuit. In other words, I need to set my time division in a manner that allows me to see at least a full cycle of my signal. A couple cycles is good, 3. More than that, it gets busy. And you can't measure as accurately as seeing a full cycle. Or 2. So, at this stage, let's say you didn't do the math. What is 60 hertz, right? What is that, 16.7 millisecond in terms of period? Well, we're going to have to prove that and see, indeed, if that's what we're going to be seeing, right? That's the nice thing about doing lab work. You get to prove some of the theory or the math that you use to analyze your circuits with. So I'm going to put 1 second here, and we're going to see what kind of signal we're going to see with our scope. I'm going to say OK. And I'm going to say OK here, so it's a .tran 1. So the attribute for this, I'm just plug it right here. You could put it anywhere. This here is just saying that you can run now a simulation, a transient simulation, that is 1 second wide. Okay? Well, let's go ahead and run it, just show you. Okay? As you can see, let me just make it as big as possible so you can see. It is 1 second wide. So, let's just look at our input signal. Remember, it's 60 hertz. How many of these cycles can I squeeze in 1 second? A lot. And notice now, if I bring my mouse over, it has changed to a probe. That is the equivalent probe for your scope. If I go to ground, notice it doesn't change. I go over here, yes, because there's a difference between it and the reference. So you're going to get something of significance right here if you click. And sure enough, if I click, here's what I get. This is what you would see on your oscilloscope if you didn't set the time division properly. That would be a lot. It's very busy. But you can tell, you can get some information out of this, that the max peak voltage is 10 volt. So it's a peak-to-peak 20 volt, right? Okay. And notice your voltage division is 2 volts per division going vertically, right? And then for each one of these division is 0.1 seconds, and I have 10 of those. What if I go 1/10 of this, right? 1/10 of this will be 0.1. And 0.1 probably is where you want to be to see at least 1, 2, 3, 4, 5 cycles, 6 cycles in there. And we can go even further down by 0.05 would be ideal. Well, let's see what 0.5 does and 0.05 will do for us. Okay, so this is a good introduction on how to use this tool. So I can go to the transient here and edit it to 0.1 now instead of 1. Hit OK. Now, notice the output does not automatically happen. You're going to have to close it and click here again. Now I could have kept it, but you need to run it. There you go. And let's see here. Notice now I'm at 100 millisecond, which is 0.1 second. And let's see what kind of signal we get by clicking here. And sure enough, I've got about 6 cycles in there. Okay, maybe I should go halfway. Right, so again, the peak voltage you could see is still 10 volts. Okay, so let me close it again. And let's go to 0.5. Yeah, why not? Let's go to 0.5. 0.05, that is. And let's run this simulation again. I wish this opened a little bigger. As you can see, it's 50 millisecond. And if I put my probe right here, here it is. Okay, much better. Let's put a grid on this. See if we could actually see a grid. View. Let's see if we could put a grid. Here you go. Right? So now, this point here is 0, 0. Let's see if we get 16.7 millisecond by being right here. And this is where my mouse is, 16.7. And notice I am at 0 volt. Notice what I need you to watch is where my mouse here, by going here, what happens. You get these coordinates of X and Y. This is fun because now you can tell I'm at 16.67 milliseconds, right? At 0 volts. That means I'm recycling. Okay? If you go over here, that will be double that as much, 33.36. Okay? So every period or every cycle, it's 16.7 millisecond. Pretty much. Okay? Good. Now, that's our input. How about our output? So we can leave our input as a point of reference and see where our output is at. I'm going to click right here. Okay? And notice I have a much lower peak value. And I've got a phase angle shift between it and this one. Now we know in theory the voltage and current in the circuit are going to be out of phase as well because you have an inductor. Okay? Great. So now let's go ahead and increase the frequency for this signal and see what happens to this blue line right here. Right? So would it ever go, and let's see what the max value is here, above 0.72 volts. Notice I have max is 0.72 volts. You could zoom in here. I don't know if you could do it from here. Zoom vertical to fit. You could do something like that. You could do a whole bunch of things. Let me see here. There, and I could zoom right here to see that I am at 0.75 volts, right there. Okay, so now let's go back, zoom to fit, and we're back to normal. Okay, pretty nifty tool. Now, let's go ahead and increase the frequency right here for this power supply. And I'm going to go by 10 times. 600 hertz. Now, if you do that, you need to go by 10 times for your transient time, or the other way around. So I'm going to say, okay, remember you've increased the frequency. Okay, let me go over here and type 0.05 to keep the same ratio. All right, let's see what happens when you run this. I'm going to hit run. Okay, and let's put a grid. So notice here I'm at 5 milliseconds instead of 50. Okay, so let's view a grid for now. View grid. All right, I guess it will show the grid once the signal is in there. Well, let's do that. Let's put the signal. There you go. Now let's look at it. That's my power source, right? The voltage at the source hasn't changed. Now let's compare it to the inductor. And let's try to understand the behavior of what we're looking at. And as you can see, at 600 hertz, what happened to the inductor's voltage? Now, notice initially, this is plain physics. It hasn't stabilized yet. It hasn't reached a point where it will stay at its steady state of almost 6 volts. So V sub L is 6 volts now, which means I have less voltage drop against the resistor. Right? Because the resistor is taking up the slack, the difference between the two. Okay, fantastic. So what if I increased it even more? The frequency. Okay, well, let's do that. And let's go to 6K. So 6K, which is 6,000, I could type K here. And if I'm doing that, remember I went up by a value of 10. Go the other way over here. And I'm going to say, okay, let's run this. Let's make this big enough to see what the result looks like. Now, as you guessed it, you've increased X of L. And if you increased X of L, because you've increased the frequency, then the voltage drop against the inductor is going to be almost as if the inductor is open, which means it's almost the source. Let's prove that. So I'm going to go to the circuit. Here's my source. And then I'm going to click here. Here is my inductor. And sure enough, notice that the two of them are getting really close, which means it's as if I have an open circuit. Okay, let's go even further and increase the frequency to 60 kilohertz. 60 kilohertz, great. Change your transient accordingly, and then add a 0 over here. Let's close this and rerun. And let's click here. And let's click here. Let me make it bigger. And as you can see, they're pretty much the same signal. That's telling me the current is almost 0, which means it's almost an open circuit, right? And indeed, because Z of L, as you increase the frequency, will increase as well, or X of L.